What if everything you knew about our place in the universe was wrong? What if our solar system isn't just rare, but utterly unique, a 1 in a billion anomaly in the vastness of space? Stick with us, because the truth might shock you and redefine our cosmic perspective forever. For centuries, humanity has grappled with its place in the cosmos. From geocentric to heliocentric models, our understanding has evolved, often pushing us further from the center of creation. Yet, a new, profound question now emerges. What if our solar system, far from being ordinary, is an extraordinary cosmic anomaly? Imagine, for a moment, that our little corner of the cosmos is not just rare, but possibly unique. What if we are living in the most exceptional system out there, a system so different from anything else in the universe that it defies what we consider normal? Could we truly be alone, not just in terms of life, but in the very architecture of our planetary home? These are not just rhetorical questions, they are the exact ones that scientists are desperately trying to answer right now. For generations, we've operated under the Copernican principle, assuming that our solar system is likely typical. The sheer scale of the universe, with its billions of galaxies and trillions of stars, seemed to guarantee that systems like ours must be abundant. But what if that fundamental assumption is flawed? What if our system is far more unique, more exceptional than we ever dared imagine? We are on the brink of discovering something that could completely rewrite everything we thought we knew about life, the universe, and our singular place within it. The Copernican principle, a cornerstone of modern astronomy, suggests that Earth is not in a special or favored position in the universe. It implies that our solar system should be fairly representative of others. This principle has guided our search for exoplanets and extraterrestrial life, leading us to expect similar planetary configurations elsewhere. However, the more we peer into the distant reaches of space, the more our observations challenge this comfortable assumption. The universe, it turns out, is far more diverse and surprising than our models predicted. The systems we are discovering often look nothing like our own, forcing us to reconsider our cosmic normalcy. This isn't about returning to an anthropocentric view of the universe. Instead, it's about a deeper scientific inquiry into the specific conditions that allowed our solar system to form and evolve. It asks whether these conditions are common or represent a rare confluence of cosmic events. The implications for the prevalence of life are staggering. Recent advancements in space exploration, particularly the advent of powerful telescopes like Kepler and TESS, have revolutionized our understanding of exoplanets. We've gone from knowing of only a handful of planets outside our solar system to confirming over 5,500, with thousands more candidates awaiting verification. This explosion of data is our primary tool for assessing our solar system's uniqueness. These missions employ ingenious methods, such as the transit method, where telescopes detect tiny dips in a star's brightness as a planet passes in front of it. Another technique, radial velocity, measures the subtle wobble of a star caused by the gravitational tug of orbiting planets. Each new discovery adds another piece to the cosmic puzzle. What these discoveries have revealed is a universe teeming with planetary systems, but many are wildly unlike our own. We're not consistently finding solar systems with small, rocky planets like Earth, followed by giant gas planets like Jupiter, all orbiting in neat, stable paths. Instead, the cosmos presents a bewildering array of configurations. We've found hot Jupiters orbiting incredibly close to their stars, super-Earths that are larger than Earth but smaller than Neptune, and systems with planets packed so tightly they almost touch. Many systems exhibit highly eccentric orbits or planets with extreme inclinations, a stark contrast to our own system's relatively orderly and circular paths. This diversity forces us to question if our solar system's architecture is truly an outlier. One of the most compelling arguments for our solar system's potential uniqueness centers on the role of Jupiter. This colossal gas giant, the largest planet in our system, is often considered a silent guardian. Its immense gravitational pull has profoundly shaped the evolution of the inner solar system, potentially making Earth's existence possible. Jupiter acts like a cosmic vacuum cleaner, deflecting or absorbing countless comets and asteroids that might otherwise have impacted Earth. Without Jupiter's protective presence, our planet would likely have experienced a far more frequent and devastating bombardment of celestial debris. This constant barrage would have made the emergence and sustained evolution of complex life incredibly challenging, if not impossible. Furthermore, Jupiter's gravitational influence is thought to have played a crucial role in sculpting the asteroid belt and the Kuiper belt. These regions, while sources of potential impactors, are also relatively stable due to Jupiter's long-term gravitational resonance. This stability is another factor contributing to the long-term habitability of the inner planets. The Grand Tack hypothesis even suggests that Jupiter migrated inward and then outward during the early solar system's formation. This dynamic movement could have cleared out much of the inner solar system's primordial debris, preventing the formation of super-Earths and allowing smaller, rocky planets like ours to coalesce. Such a precise and impactful migration event might be incredibly rare. When searching for life, scientists often focus on the habitable zone, the region around a star where temperatures allow for liquid water on a planet's surface. This concept, while crucial, is increasingly understood to be far more complex than a simple distance calculation. The uniqueness of our solar system might extend to the very conditions that define our habitable zone. For instance, the presence of a large moon like ours, which stabilizes Earth's axial tilt, is thought to be vital for long-term climate stability. Without the moon, Earth's tilt could wobble chaotically, leading to extreme and rapid climate shifts that would hinder the development of complex life. Such a large moon, formed from a giant impact, might be another rare cosmic lottery win. Moreover, the composition of a planet's atmosphere, its geological activity, and the presence of a strong magnetic field all play critical roles in maintaining habitability. Earth's plate tectonics, for example, helps regulate its carbon cycle, preventing runaway greenhouse effects or ice ages. These intricate planetary processes are not guaranteed even within a star's habitable zone. The type of star also matters. Our Sun is a relatively stable G-type star, providing consistent energy for billions of years. Many exoplanets orbit red dwarf stars, which are prone to violent flares that could strip away planetary atmospheres, even if the planets are in the habitable zone. Thus, our Sun's benign nature is another factor contributing to our system's unique habitability. The European Space Agency's Gaia mission is poised to provide unprecedented insights into the architecture of planetary systems within our galaxy. Gaia is meticulously mapping the positions, distances, and motions of nearly 2 billion stars in the Milky Way. This incredible dataset will allow astronomers to precisely measure the tiny wobbles of stars caused by orbiting planets, especially those with long orbital periods. For the first time, we might get an in-depth, statistically significant look at solar systems in our galactic neighborhood. Gaia's precision will enable the detection of Jupiter-like planets in wider orbits, which are much harder to find with current transit methods. This will give us a more complete picture of planetary system architectures, moving beyond the hot Jupiters that dominate current exoplanet catalogs. What if Gaia reveals that solar systems similar to ours, with widely spaced, orderly gas giants and inner rocky planets, are far rarer than we expected? Or, conversely, could it prove that there are countless other systems out there that follow the same structure, perhaps even with similar grand tack events? The data from Gaia could be the definitive answer to whether our solar system is truly an anomaly or a common blueprint. The implications of Gaia's findings will be profound. If our system proves to be statistically unique, it would lend significant weight to the idea that the specific conditions required for complex life are exceedingly rare. If, however, Gaia shows that our architecture is more common, it would bolster the argument for widespread life. We are about to find out. If our solar system truly is a cosmic anomaly, what does this mean for the existence of life beyond Earth? The rarity hypothesis suggests that the specific combination of factors that led to Earth's habitability and the emergence of complex life might be incredibly improbable. This includes not just the planet itself, but the entire system's configuration. A unique solar system architecture, with Jupiter's protective shield, a stable star, a large moon, and plate tectonics, could mean that Earth is not just a habitable planet, but a super-habitable one. This confluence of factors might be so rare that finding another planet capable of supporting complex, intelligent life becomes an astronomically difficult task. This perspective doesn't necessarily mean we are alone in the universe. Simple microbial life might still be common, thriving in less ideal conditions. However, it would suggest that the conditions for the long-term stability and evolution required for multicellular organisms, and eventually intelligence, are far more stringent and unique than previously thought. The search for extraterrestrial intelligence, SETI, would then take on an even more poignant meaning. If our solar system is a rare jewel, then any intelligent civilization arising within a similar, improbable system would be an even more precious discovery. It would underscore the incredible odds overcome by life, both here and elsewhere. The potential uniqueness of our solar system also offers a compelling perspective on the Fermi paradox. This paradox asks, if the universe is so vast and ancient, and life is common, then where is everybody? Why haven't we detected any signs of advanced extraterrestrial civilizations? If our solar system's architecture is indeed a rare occurrence, it could provide a partial answer to the Fermi paradox. Perhaps the great filter, the hypothetical barrier that prevents civilizations from emerging or expanding, lies not just in the development of life itself, but in the very formation of a stable, long-lived planetary system capable of nurturing it for billions of years. A unique solar system, with its specific protective mechanisms and long-term stability, might be a prerequisite for life to evolve beyond simple forms. This would mean that the number of Earth-like planets capable of supporting advanced civilizations is far smaller than we once imagined, making encounters with other intelligent species incredibly unlikely. This thought is both humbling and awe-inspiring. It suggests that our existence, and the existence of our solar system, might be a truly precious and improbable cosmic event. It places a profound responsibility on us to cherish and understand this unique home we inhabit. The quest to understand our solar system's place in the universe is more than just an academic exercise. It's a fundamental inquiry into our origins, our future, and our potential cosmic solitude. Every exoplanet discovered, every stellar wobble measured, brings us closer to answering this profound question. Whether our solar system proves to be a common blueprint or a singular masterpiece, the journey of discovery continues. The data from missions like Gaia, combined with future observatories like the James Webb Space Telescope, will continue to refine our understanding. We are living in an unprecedented era of cosmic exploration, where the answers to humanity's oldest questions are finally within reach. This ongoing scientific endeavor is a testament to human curiosity and our relentless drive to explore the unknown. It reminds us that the universe is full of wonders, and the truth, whatever it may be, is always more fascinating than our initial assumptions. Our understanding of our cosmic address is constantly evolving, and the next revelation could be just around the corner. Now, before you ponder the vastness of space, don't forget to hit that subscribe button and ring the notification bell. By subscribing, you'll support our channel and encourage us to create even more exciting videos that will take you further into the wonders of the universe and the cutting edge of scientific discovery. Question for you: do you think our solar system is truly unique, a rare cosmic gem, or do you believe there are countless others like it in the universe, waiting to be discovered? Let us know your thoughts by commenting A for our solar system is unique, or B for there are many solar systems like ours. We'd love to hear from you and get the conversation started. Welcome, cosmic explorers, to Stellar Insights, your weekly journey into the heart of astronomical discovery. Today, we embark on part 2 of our epic quest, unraveling the ingenious methods humanity employs to find worlds beyond our wildest dreams. Prepare to be inspired as we peer into the cosmic tapestry, searching for answers to the universe's most profound questions. As humanity stands on the precipice of a new era of space exploration, our understanding of the universe is undergoing a dramatic shift. For millennia, we've gazed at the stars with wonder, but our ability to truly explore beyond our own solar system has only recently become a reality. The profound question of whether our solar system is an outlier or just one among countless others in the cosmos has captivated scientists and dreamers for generations. But how do we even begin to search for an answer to such a monumental question? How do we look for life, or signs of systems like our own, when the universe is so vast, so overwhelmingly complex? The truth is, finding planets outside our solar system, known as exoplanets, is no easy task. These distant worlds are often billions of times fainter than their host stars, making direct observation nearly impossible. Early efforts were limited, using indirect methods that could only provide a fleeting glimpse of what was out there. Yet, with unwavering determination, scientists have developed an array of sophisticated techniques to overcome this immense challenge, each bringing us one step closer to answering if our solar system is truly unique. One of the most foundational methods in the search for exoplanets is the Doppler shift technique, also known as the radial velocity method. This ingenious approach leverages a fundamental principle of physics, the gravitational tug that planets exert on their stars. As a planet orbits, its gravity causes the star to wobble ever so slightly. While this stellar movement is incredibly subtle, it is enough to be detected by observing the shift in the light emitted by the star. As the star moves toward us, its light waves compress, shifting to shorter, bluer wavelengths. Conversely, as it moves away, the light waves stretch, shifting to longer, redder wavelengths. By meticulously measuring this minute shift, astronomers can infer the presence of an unseen companion. This technique allows us to calculate the planet's mass and orbital period. The Doppler shift method was instrumental in discovering many of the first exoplanets, particularly massive gas giants orbiting close to their stars, revealing a universe far more diverse than we ever imagined. Detecting exoplanets using Doppler shifts, however, has its limitations. It is more sensitive to large planets that orbit close to their stars, as their gravitational influence is more pronounced. This means smaller planets, like Earth, or those with longer orbits, are much harder to detect using this method alone. This is where the next revolutionary breakthrough in exoplanet discovery comes into play, the transit method. The transit method relies on a completely different, yet equally brilliant, approach. When a planet passes directly in front of its star from our vantage point, it blocks a tiny fraction of the star's light. This causes a temporary, periodic dip in the star's observed brightness. If this dimming happens regularly, it signals that the star is being orbited by a planet. This method is incredibly effective for detecting planets, especially those in the habitable zone of stars, where conditions might allow for liquid water. The Kepler Space Telescope, launched in 2009, revolutionized the field by monitoring the brightness of over 150,000 stars in a small patch of sky. Its unparalleled ability to detect the faint dimming caused by transiting planets led to the discovery of thousands of exoplanets, including many Earth-sized worlds within their stars' habitable zones, igniting our hopes for finding life beyond Earth. Yet, the transit method also has its own set of challenges. It only works when the planet's orbit is perfectly aligned with our line of sight, meaning many potentially habitable planets could be missed. To overcome these challenges and paint a fuller picture, scientists have turned to a third, incredibly precise method: astrometry. Astrometry, the ancient science of measuring the positions and movements of celestial objects with incredible precision, offers a powerful tool for detecting exoplanets. Instead of looking for the Doppler shift in light or a dip in brightness, astrometry directly measures the actual, tiny wobble of the star across the sky. This wobble is caused by the gravitational pull of an orbiting planet. This technique is particularly useful for detecting large, Jupiter-like planets that orbit far from their stars, where their gravitational influence creates a more noticeable shift in the star's position over long periods. By meticulously tracking a star's position over time, scientists can detect the subtle, periodic shifts caused by the gravitational pull of a distant planet. The Gaia mission, launched by the European Space Agency, is a marvel of astrometric precision. With its unprecedented accuracy, Gaia is capable of detecting exoplanets that other methods might miss, offering a new window into the architecture of planetary systems. Beyond the direct interactions of star and planet, the universe itself can act as a lens. Gravitational microlensing is an extraordinary method that harnesses the fabric of space-time. When a foreground star, acting as a massive lens, passes almost perfectly in front of a more distant background star, its gravity bends and magnifies the background star's light. If an exoplanet orbits the foreground lensing star, it creates an additional, brief spike in the magnified light curve. This fleeting event, lasting from hours to days, reveals the planet's presence. Microlensing is uniquely powerful for finding planets at vast distances, even rogue planets not orbiting any star, and those in orbits too wide for transit or radial velocity methods. It offers a glimpse into the colder, outer reaches of planetary systems, expanding our understanding of planetary formation far beyond our solar neighborhood. Finally, the ultimate dream, directly seeing an exoplanet. Direct imaging is the most challenging, yet potentially most rewarding, method. Imagine trying to spot a firefly next to a lighthouse from hundreds of miles away. That's the scale of the challenge. Stars are billions of times brighter than their planets, completely overwhelming any planetary light. To achieve this, astronomers employ sophisticated instruments like coronagraphs, which block out the blinding light of the host star, and adaptive optics, which correct for atmospheric distortions. This allows them to capture the faint, reflected or emitted light from the planet itself. Currently, direct imaging is primarily successful for very large, young, and hot gas giants orbiting far from their stars, as these planets are brighter and more easily separated from their host star's glare. While still in its infancy, direct imaging holds immense promise for the future. It allows for direct spectroscopic analysis of exoplanet atmospheres, searching for biosignatures, chemical indicators of life. This method is our clearest path to truly seeing another world and potentially finding evidence of life beyond Earth. Together, these diverse methods form a powerful, complementary toolkit for exploring the cosmos. They allow us to look beyond our solar system and find planets that could one day harbor life, or at least reveal the incredible diversity of planetary systems. But they also raise a deeper, more profound question: what does it mean for us, as humans, to be able to look out into the vastness of space and begin to unravel the universe's deepest mysteries? The discovery of exoplanets is not just a scientific achievement, it is a testament to the boundless potential of human curiosity and the infinite possibilities that lie ahead. Each new world found is a beacon of hope, a reminder that our universe is far richer and more complex than we ever dared to imagine. As we continue to refine these methods and gather more data, we are getting closer to answering the ultimate question: are we truly alone in the universe, or are there countless other worlds out there, waiting to be discovered? The search for exoplanets is not just about finding new worlds, it is about finding our place in the cosmos. It is about exploring the unknown and understanding that, no matter how vast the universe may seem, our curiosity and determination can bring us closer to the answers we seek. Don't miss a single cosmic revelation. Subscribe to Stellar Insights wherever you get your podcasts, share this episode with fellow astronomy buffs, and join our online community to discuss the latest exoplanet discoveries. Your journey into the universe has just begun. For millennia, humanity has gazed at the stars, pondering our existence. Are we alone in this vast cosmic ocean, or do countless other worlds mirror our own? This profound question, etched into our very being, now stands on the precipice of an answer, thanks to a revolutionary mission that is reshaping our understanding of the cosmos. From the dawn of civilization, the night sky has been a canvas for our deepest questions. Ancient astronomers charted constellations, weaving myths and meaning into the celestial tapestry. They wondered if other suns harbored worlds, if other beings looked back at them. This innate curiosity, this yearning to understand our place, has driven centuries of scientific endeavor. It's a journey from simple observation to sophisticated instruments, each step bringing us closer to the truth. We are not just observers, we are active participants in this grand cosmic quest. For much of history, the idea of planets beyond our solar system remained a dream, a whisper in the dark. But in recent decades, that dream has blossomed into reality. We've discovered thousands of exoplanets, each a testament to the universe's boundless creativity. Yet, many of these discoveries have been of systems vastly different from our own. The question persists, where are the solar systems that truly resemble ours, with their delicate balance and potential for life? This is where a new vision, a new frontier, emerges. Enter Gaia, the European Space Agency's extraordinary space observatory. Launched with a singular purpose, Gaia is not just looking for planets, it's meticulously mapping the Milky Way, charting the positions and motions of over 1 billion stars with unprecedented precision. It's creating the most accurate 3D map of our galaxy ever conceived. This isn't just about pretty pictures, it's about understanding the fundamental dynamics of our cosmic neighborhood. Gaia's revolutionary technique, called astrometry, allows it to detect the tiniest wobbles in a star's movement. These subtle shifts are the telltale signs of orbiting planets, even those far from their parent stars. Imagine a star, seemingly fixed in the heavens. But if a massive planet orbits it, that planet's gravity will tug on the star, causing it to subtly sway. Gaia's instruments are so sensitive, they can measure these minuscule movements, revealing the presence of unseen worlds. This is how Gaia can find planets that other methods often miss. This precision is critical for finding systems like ours. We need to detect gas giants, like Jupiter, in their wide orbits, as they play a crucial role in shaping a solar system's architecture and protecting inner, potentially habitable planets. Gaia offers us the best chance yet to find these cosmic guardians. The data Gaia collects is a treasure trove, a digital key to unlocking cosmic mysteries. With each data release, scientists around the globe gain access to an unparalleled wealth of information. The upcoming 4th data release, scheduled for December 2026, promises to be a watershed moment. It's expected to reveal thousands of new exoplanets, many of which could reside in systems strikingly similar to our own. This deluge of data will allow us to analyze the dynamics of distant solar systems in ways previously unimaginable, moving us closer to answering the ultimate question. What if Gaia finds a solar system with a gas giant like Jupiter, orbiting at a similar distance to its star? What if it hints at rocky planets nestled in the habitable zone, where liquid water could exist? Such discoveries would be nothing short of revolutionary. They would provide tangible evidence that our solar system might not be a cosmic anomaly. This isn't just about finding another planet, it's about finding a cosmic twin, a system that echoes the familiar patterns of our own. It would suggest that the conditions necessary for life, as we understand it, might be more common than we ever dared to imagine. The quest for other solar systems like ours is more than a scientific endeavor, it's a profound philosophical journey. It forces us to confront our own uniqueness, or perhaps, our commonality. If we find that systems like ours are rare, it might underscore the preciousness and fragility of life on Earth. Conversely, if Gaia reveals a multitude of similar systems, it could ignite a new sense of wonder and possibility. It would suggest that life, in its myriad forms, might be a natural and widespread phenomenon across the universe. This search is a mirror, reflecting our deepest hopes and fears about our place in the grand scheme of existence. Gaia's mission is a testament to the enduring human spirit of exploration. It embodies centuries of curiosity, from the first stargazers to the brilliant minds designing and operating this incredible observatory. It reminds us that our desire to understand, to push the boundaries of knowledge, is an intrinsic part of who we are. Every piece of data, every new discovery, is a step forward in humanity's collective journey. It connects us to those who dreamed of other worlds and inspires future generations to continue this magnificent quest. We are not just mapping stars, we are charting the course of human destiny. Are we truly alone? Or are there countless other solar systems out there, waiting to be discovered, perhaps teeming with their own unique stories? This is the question that defines our era of space exploration. With Gaia leading the way, the answers are closer than ever before, promising to redefine our understanding of life, the universe, and everything. This journey of discovery is a powerful reminder of the limitless potential of human curiosity and ambition. It's a story of pushing boundaries, seeking answers, and embracing the unknown. The universe is full of mysteries, but it is also brimming with the possibility of wonder, and our journey has only just begun. If you've been inspired by this incredible exploration into the cosmos, don't forget to subscribe to our channel. Your support fuels our mission to bring you more thought-provoking content, keeping the spirit of discovery alive. Join us as we continue to unravel the universe's greatest secrets.